Test. Hi, Tavi. Can you hear and see everything good?
Yes, sir, I can.
Okay, good. All right. Well, no, not yet. There we go. Okay. So we have a test on Monday, and I sent the review. And there was one part on that review at the very end where I said, inequalities, go look at your homework. I didn't put any problems there, just expect that there would be something over inequalities on the test. So something similar to the homework. Were there any questions on anything homework wise or anything you want me to go over? So what are y'all expecting in terms of, I gave you a review. I'm guessing you're going to want solutions. Last time y'all wanted them on video, right? Someone requested them on video. So didn't I do them on video last time? I'll try and do the same thing. I don't want to get you used to that because I know like in pre-cal, Cal 1 is very unlikely that you're going to have, well, in calculus, you may not even get a review. So if you do, I don't want you to be like, well, you know, in algebra, they worked out all the review on, you know, it's just not something I would expect down the road. I don't mind doing it, but see how much of it you can get done on your own. And I'll try and work on that this weekend. Someone remind me if Saturday comes and there's no review answers or anything, someone send me an email or a text. Okay, we are going to talk about function. Well, we started talking about composition last time after we did inequalities, and we want to continue with this idea of composition. This will not be on the exam, okay? Well, yeah, I said I wouldn't put today's stuff on the exam, right? So this will not be on the exam, but important nonetheless. All right, so here we go. Everything I put up here today, I will send you a copy. So I don't want you to sit here and feel like you have to write every little thing down because there's a lot of stuff I wrote already. I will send you a file that'll have all this stuff. So first of all, let's just take a step back. When we talk about a function, when we're given a function f of x, right? The idea is that we can plug something into this function, it's going to spit something out, right? And the things that we plug in, all the things that are valid to plug into the function comprises what's called the domain of f, which we can abbreviate DOM-f. And then the things that come out of the function, all the outputs, is called the range of f or RAN-f, right? So that's just a visual representation of what a function looks like in general, right? So for example, if we take the function x squared, then we're going to plug some x's in, and then it's going to spit out whatever x we plug in squared. So if I ask you to talk about the domain of this function, what you have to do is look at x squared and say, hey, is there anything I can't plug in? Well, x squared is not, you don't see a square root there, right? Remember, we can't do square roots of negative numbers. So there's no square root here. Also, there's no fractions. So we have to always be careful for division by 0 and square roots of negative numbers. Here we don't have either one. So that means the domain of this is anything. The domain of f is all real numbers, everything between negative infinity and infinity. This all makes sense? Now the range is a little bit tricky because you're going to be taking numbers in and squaring them. And when you square a number, it's impossible to get a negative, right? You can't get a negative out. Now, can you get 0 out? Yes, because if you plug 0 in, 0 squared is 0, right? So it is possible to get 0 out. So my range is 0 and then everything positive. And you could kind of confirm this since we know what this function looks like, right? If we were to graph x squared, we know that it looks like this. And just by looking at that graph, you could tell me the domain is everything because left and right, you have picture. And then the range is everything from 0 up. So from 0 to infinity, right? Okay, so there's nothing new here, right? Just want to make sure we're solid on the notation and what the domain and range mean. Here's another example. If we take f of x as the square root of x, now we have some issues, right? This function is going to take in values, spit out the square root of the value, but we can't plug negatives in. So my domain is going to be from 0 to infinity. We can take the square root of 0, right? Square root of 0 is 0. You just can't do a negative number. So anything from 0 to infinity can be plugged in. And then what about the output? The output is also 0 to infinity. How do I know that? Kind of two ways to look at it. If I plug in a positive number, the square root of a positive number has to be positive. If I plug in 0, of course, the square root of 0 is 0. But there's no way to get a negative answer out of this because this square root always spits out positives. Another way to look at it would be if you knew what the graph looked like. And remember, the square root of x is a function you should know what it looks like. In fact, on your review, I ask you to graph a square root function using transformations. So everyone should know here that the standard square root function looks like this. And if you look at, well, kind of like that, it's not so steep, but the general feel for it is this. The domain is everything from 0 to the right, right? You've got function to the right of 0, including 0. And the range is everything from 0 up. So that's where these two come from. We still good? Okay. Trust me, we're building to something here, okay? This last function that we're going to look at, f of x equals 1 over x minus 2. What kind of function is this? Have we studied these? That's a rational function, right? Which means you could graph it if I asked you to. Well, I could ask you to graph it. I don't know if you could graph it, but I could ask you to graph it, right? So let's talk about this one. It takes things in, spits out 1 over x minus 2. Well, there's one number I can't plug in, right? And that's 2. So my domain is everything to the left of 2, everything to the right of 2. I cannot include 2, right? So there's my domain. Now look at my range. Everything except 0. How did I get this? I have a horizontal asymptote. So you have to kind of know what this function looks like, which means you might have to do a quick little rundown of a sketch of it. Let me show you how I would do it real quickly. The first thing I would do is I would factor the top and bottom. I'm just going through the steps for graphing a rational function. Factor the top and bottom. It's already factored. I have no holes. Then I look for what makes the numerator 0. Well, the numerator is 1, right? 1 is never 0. So I have no what? No x-intercepts. Okay. Then I look at what makes the denominator 0. 2, right? So now I know I have what at 2? What do I have? Yeah. Are you okay? I could tell. I just want to make sure you're here. All right, so the vertical asymptote at 2, right? And then I look for the horizontal, right? I compare the degree of the top and the bottom. So what's the degree of the top? 0, because there is no x. The bottom, 1. That means the degree of the top smaller than the bottom. That means the x-axis, right? So I should expect an x-axis like this. And that's it. I just need 2 test points. 2 test points. That's all I need, right? So I could plug in, let's say 0. What would happen if you plug 0 into this? You get a negative number. So I know that my graph is like down here somewhere. And then over to the right of 2, pick a number like 3 maybe, plug 3 in here, I get a positive number. And now I know it goes up, it flattens out. Over here, it flattens out and goes down forever. So the range of this, right, is everything except it never hits the x-axis. So it's everything except 0. So this little answer here that I just kind of threw up here without the picture is not so simple to get. You actually have to understand how this thing is behaving. Also, just to be careful on this, the horizontal asymptote was the x-axis, right? That would not alone tell us that we don't ever hit 0. So let me just give you an example. If I would have had x plus 3 over x squared minus 4, let's say I had that as my function, then the horizontal asymptote is the x-axis, right? Because the degree of the top is smaller than the bottom. But I do have an x-intercept at -3, right? So this actually would, I just want to make sure, because you have to check more than just the horizontal, because it might cross through somewhere else. Okay. All right, with all that in place, okay, this is just the general idea of functions, domains, and ranges. Let's go revisit the idea of composition. I'm going to have to zoom out just a little bit here. So when we were talking about functional composition last time, what we said is if we're given 2 functions, we can do this thing with the functions that you can't do with numbers, right? This composition. So if you're given 2 functions, f and g, we have 2 standard compositions, even though I did tell you you can compose functions however you want. You can do f with itself 20 times, but the 2 standard ones are you compose f of g of x. That means you take x, plug it into g, then take that answer, plug it into f. Or you could do the other way around, where x goes into f first, and then that answer goes into g. This is a visual representation of those 2 processes. So for f of g of x, x first goes through g, right? Comes out as g of x. That answer then goes through f and comes out as f of g of x. So that's the visual representation. Here's the part I want you to really pay attention to. As x goes into g, right? Everything in here is the range of g, isn't it? It's the things that come out of g. But those also turn out to be the domain of f. These outputs from g wind up being the inputs of f. All right, that's critically important here in a minute. So x goes into g, that answer goes into f. Here, with the other composition the other way, x goes into f first, that answer goes into g. So the domain of f are these values, but the range of f, right, the things that come out, becomes the domain of g. So x goes into f, that answer goes in g. If this is still a little unclear, don't worry, I'm gonna make sure you understand this. I'll refer back to that. So let's talk about the domains of composition of functions. If we look at f of g of x, so all we're going to look at is this one right now, this one here. Okay, what is the domain? Okay, so what is the domain of composition? Well, first of all, in order for this to make sense, do you all agree that I need to make sure that I don't plug any x's in that are going to screw up g? Right? So I've got to make sure the x's I plug in don't mess up g. That's the first thing. All the x's in the domain of g would be part of the domain of f. Okay? We need to check g for any issues. The next thing, and this is the tricky part, is that we need to make sure that all the g of x's, the things that come out of g, are in the domain of f. That these outputs don't mess up f. That's going to be a little harder to do. So to do this, we need to see when G creates issues for F. And now we're going to do some examples, all right? So let's look at our first example here. If f of x equals the square root of x and g of x equals x minus 2, let's first find the composition f of g of x, and then let's find its domain, all right? So let's do the actual algebraic computation first. We're going to figure out what f, let me do this in different color. We're going to first figure out what f of g of x is. So the definition of this is that you take f and inside of it, you plug in the g, right? For us, g of x is the function x minus 2, right? So all I'm doing there is replacing g of x with x minus 2 because that's what it is, right? And then we take that expression in green and we plug it into the f function. So what should I get here as my final composition? Square root of x minus 2. Everyone clear on that? Square root of x minus 2. That is the composition. Taking this x minus 2, sticking it right in here for x, which means replace that x with x minus 2, and you have your final composition. So that is the answer to the first part. Now, what is the domain of this? Can you tell by just looking at this? Maybe. Maybe you can. But the way we're going to do it is we're going to do it in two different phases. The first thing we're going to do is we're going to check out what g is, right? Because g was the first function. So if we look at g, what is its domain? What's the domain of g? Is there anything you can't plug into this? No, you can plug anything you want into that, right? There's no division by 0. There's no square roots. Everything's good. So domain of g, all real numbers, negative infinity to infinity. So far, it looks like I can plug anything in, right? So far, it does. However, we need to now look, does G ever spit out something that F can't handle, right? Is there something that G spits out that F can't handle? Well, what is the F function doing? Taking the square root, right? So it's taking the square root of what? Not x, but x minus 2, right? So what do we need to make sure about this x minus 2 that's going to go into f?
It can't be a negative number.
Can't be negative, right? Can't be negative. So this second step, what I'm checking is what, output of G creates problems for F. All right. So what we need in order to make F okay is we need that x minus 2 can't be negative, right? Can't be negative. Another way of saying that is it must be positive or 0, right? To say that something can't be negative is the same as saying it has to be greater than or equal to 0. And what type of inequality is this? Linear, right? And those are the easiest to solve. Just add 2 to both sides. Right? Greater than or equal to 2. So according to the second step, we need to make sure that our domain is everything bigger than 2. Your final answer is whatever both steps 1 and 2 have in common. So the first step says, hey, you can be anything you want, right? But the second step says, no, we need to make sure that x is bigger than or equal to 2. So your domain will be x bigger than or equal to 2. Now, you probably could have told me that just by looking at this right here, okay? But it's not always that easy to just look at that and know. You have to think of these two kind of processes. Okay, so our final answer is domain is all values greater than or equal to 2. All right, so what I have highlighted here in yellow would be the two parts of the answer to that. First of all, what is the composition? It's down there, square root of x minus 2. What is the domain? It's right there. Questions? We good? Hold on. Wait a minute, is that the same problem? No, it's not the same problem. I switched it on you. See that? I did g of f of x. So do we have the same domain? Do you think it changes if we change the composition? It does change. Let's see how, okay? Now, sometimes it will be the same domain. Sometimes, you know, it won't. Most of the time it won't, but let's just see. By definition, g of f of x means we're going to take the g function. Inside of that, we're plugging in the f function. So I replace the f function with the square root of x. And then I replace the x in the g function with the square root of x. So what should this be? Square root of x minus 2. But now this time it's different, right? Because this square root does not extend over that minus 2, right? It's the square root of x and then take away 2. The previous one was the square root of the whole quantity x minus 2. Those are two different expressions. Okay? So let's talk about the domain of this. What's the first thing we're going to need to look at? The domain of what? Who got x first, right? F got x first. So we need to look at the domain of f. Well, what's the domain of f? Go back up and look here. Here's f, right? Well, there's some things we can't plug in here, right? We need to make sure here that x is greater than or equal to 0. We have problems, right? Another way of saying that is that we have to be bigger than or equal to 0. So bracket 0 to infinity. That would satisfy the f function, right? Now look at the second function here, g. Is there anything that we cannot plug into this? No, there's no issues, right? There's no issues. So there's nothing that could ever come out of f, right? F is going to get the x first. There's nothing that could ever come out of this that's ever going to cause a problem with g, because g never has problems, right? It's nice, it'd be nice to be g, right? To not have any problems. Okay, but this g doesn't have any problems. So from this step, no issues, right? No issues. So what's our domain? For the second part, you could say that since we have no issues, all you have to do is really look at the first part. That's where we have issues. So our ultimate domain here is 0 to infinity. So our two answers are this is our composition and then this. These first two have been pretty straightforward. There's not a whole lot of craziness happening here. The next one is going to be a little weird. Any questions though? Okay, I want you to look at f of g of x and then find its domain. So let's start off with the algebra. F of g of x means f inside of f goes g. Okay, f inside of f goes g. I replace with 1 over x minus 2, right? And then that goes into f. So what does f do to this? Takes the square root of the whole thing. Right? Now, let's look at the domain. I'll start out by looking at the domain of what first? Who got x first? G. So I'm going to look at the domain of G. What is the domain of G? Everything but 2, right? Everything but 2. So just x can't be 2 here. The way we do that in interval notation, everything negative infinity to 2, union 2 to infinity. So far, here's what I know. Can't plug 2 in, right? Can't plug 2 in. Now the tricky part. We have to look at the output of G going into F, right? So the output of G is this, right? That's going to go into F right there, which really gives us this, right? So we have a square root of all this junk right here. What do we have to make sure happens? That this right here is what? Is not negative, right? We need to make sure that this in here is not negative, which means that we need to make sure that 1 over x minus 2 is greater than or equal to 0, right? Greater than or equal to 0. How are you going to determine that? Isn't that a rational inequality? Wasn't that part of your homework assignment? Right? So now I did this problem earlier for us, right? That's why I did it earlier. Remember when I showed you this right there? And we graphed it. Can we tell from this graph where it's greater than or equal to 0? Where? Where's this graph? Where's the graph of that function greater than or equal to 0? Where it's above the x-axis, right? It never touches the x-axis, so we don't have equal, do we? But it's, where is it above the x-axis?
From 2 to infinity.
From 2 to infinity, to the right of 2. Okay, to the right of 2. Which means that to answer this question, right? We would have to look at its graph and realize that this little graph has that vertical asymptote, right, at 2. And over here, a little horizontal, and then my little graph is above the x-axis over here. That's to the right of 2. Do we include 2? No, because you have vertical asymptote there, right? Plus, this tells us you can't have 2 anyway, right? But this would tell us everything to the right of 2. So it would be from 2 to infinity. Now we have to combine these two answers together. This says, hey, look, everything except 2, right? Everything except 2, which would mean everything to the left of 2 and everything to the right of 2. This is saying just x's to the right of 2. So our answer is what they have in common. So it would be just to the right of 2. It's kind of like where they overlap, if you want to think about it that way. Here's our composition. Here's our domain. See, this can be a little tricky because when you look at this domain right now, according to this domain, I can plug in 3, right? 3 works. So if I plug 3 into this, I get 1 over 1, and that answer goes into F. The square root of 1 is 1. Here, though, 1 doesn't work, does it? 1 doesn't work. If I try and plug 1 in here, don't I get a negative number? And then if I try and plug that into here, I can't take square root of it. So the thing that you have to be careful with is that you cannot look at these domains individually, right? You can't. You can't say, oh, x can't be 2. Oh, x has to be greater than or equal to 0. You can't do that because this function only cares about the outputs of this function, not the inputs. Hope that makes sense. All right. Why don't you see if you can at least get the g of f of x written down here? I'll give you a moment. All this is flipped over, right? This is the other composition, g of f of x instead. Try and find the domain if you can. That should be g of f of x. What about domain? What do I look at first? Domain of which function? F, right? So tell me about the domain of f. Can't be
Zero.
negative, right?
Infinity.
Greater than or equal to 0, right?
Yes.
And it can be 0, right? Because you can take the square root of 0. So this would be everything to the right of 0. Okay. Now, again, this is the tricky part. We need to figure out what's going to screw up G. Tell me what's going to screw this up. If this thing down here, right? If this whole denominator becomes 0, right? But what are we replacing the x with? The square root of x, right? That's what's going to go in here. So what we need to make sure is that the square root of x minus 2, we need to make sure that that's not 0. Right? This function f plugged in right here, that's basically this down here. This can't be 0. So if I want to know where something isn't 0, I'm going to go figure out where it is 0, and then I'm going to throw those answers out. So I'm going to go figure this out by doing square root of x minus 2 equals 0. Anybody recognize what type of equation that is? We did these way in the beginning. There's like a set of steps to do these. You know? Square root, it's a square root equation, right? The first thing you do is isolate the root. Get the root by itself on one side of the equation. Then what? You square both sides. And as soon as you do that, you need to remember that you might have extraneous solutions. So you're gonna have to check your answers. Does this sound familiar now? Okay, so I'm gonna square both sides. Little note to myself, I better check my answers here. So when you square the left, you get x, square the right, you get 4, right? Not plus or minus, right? You don't do plus or minus. You only do plus or minus when you take the square root on both sides. When you square both sides, it's just whatever it is squared. So it looks like I only have one answer, right? 4. Let's just check it real quick. Does 4 work here? If I plug in 4, square root of 4 minus 2, that's 0. Okay, so that does work. So the solution is correct. But remember, we don't want this, right? We don't want this to happen. So we need to throw this out. We don't want x to be 4. So now we have to combine both of these answers together. This says, okay, yeah, anything greater than or equal to 0 is great. This is saying except 4, right? Except 4, you can't have 4 in there. So our domain would be, how do we write it? 0 to 4, so bracket 0, 4, parenthesis, union, 4 to infinity, like that. There we go. There you go. So again, I'll just point out, if you look at these functions individually, the domain of this is everything greater than or equal to 0, right? And this is saying everything except 2. But that's not our answer. Our answer is not everything greater than 0 except 2. Our answer is everything greater than 0 except 4. And that's why these compositions, you just have to be real careful about which function's going into which. All right? Any questions? We'll have an opportunity to practice these more. All right, switching gears a little bit. We're going to talk about a unique situation. And this is actually going to come up in the next section, but this section, we talk about it now. All right, I'm going to talk about a unique situation, meaning this does not always happen, okay? But sometimes it does. And what does it mean when it does? Something special is happening here. So let's say you're given two functions, right? And what if this happened when we did f of g of x? So let's say for these two particular functions I give you, we take the x, so f of g of x means that g gets it first, right? So let's say I take some x, I spit it in, or I put it into g, it spits out an answer. I take that answer, I plug it into f, and it spits out an answer. And what if I tell you that that answer is x? In other words, you started with x, it went through the two machines, and then came out itself. So that would be like, remember last class when I split up the class and I said, let's plug in a number here and do that thing? What if we did that, and every time we went through the loop, right? If I said, here, let's start with 2, 2 went through and then came out 2. Then I said 5 and it came out 5. 10 came out 10, -5. What if that happened? Is that special? I don't know. Maybe it is. Maybe it isn't. Maybe it is. Maybe it isn't. But it would be different than what we've seen, right? It seems like anytime we do composition, things get changed a lot. I like to think about it like a car wash. You know, you take this car, it's dirty, you put it through a car wash, right? And it's clean. And then you put it through another wash, it comes out dirty again, right? So it's like, is that something special? I don't know. All right, so what happened here is x went through g, then it went through f, and it came out itself, right? If that happens, couldn't we rewrite these three circles almost like this? Like the x started out, went through g, but then f took that answer right back to x. This would be a different sort of way of notating what happened through that composition. It'd be like a little loop, right? Change it, unchange it. Change it, unchange it. That's what happened. So that would be somewhat different than what we've seen. Well, what if it also worked the other way? What if, okay, so the first way was f of g of x, right? What if it also worked when we did g of f of x? So what if we take an x, plug it into the f function first, take that answer, put it into the g, and it comes out unchanged again? Would that be something special? So again, like last class, remember there were two functions. So I could have gone a number through one way and out through the other, or I could have gone through the other side and come out. This is saying, what if both directions, whatever you put in comes out unchanged? So 2 through comes out as 2. And if I do 2 this way, it comes out 2. Is that something special or not? Here's a picture of what we're looking at. X goes through F, gets changed, and then G unchanges it, takes it right back. So we could say, if this was true, right? If this happened, then we could say that X is equal to the composition, right? Because when you take X and you send it through both, it comes back itself. And it doesn't matter if you do it, you know, f of g of x or g of f of x. This turns out to be very special, all right? And we're going to talk more about this next class. Does anyone know what this means? I mean, some of you I know have done this already. Does anyone know what it means when you have a function, two functions, and they undo each other? What they're called? They're called inverse functions. They're is that what you said? Inverses. They're inverse functions. They are functions that undo each other. So it's like, oh, I'm going to clean the car, and this other function says, I'm going to put all the dirt right back where it was, you know? And in mathematics, inverse functions are very, very useful because you need a way to undo a function sometimes, right? I think one natural question would be, does every function have an inverse? Do you think every function has a function that undoes it? What do you think? Yeah, I mean, it seems like maybe, right? Okay, so let me see if I can convince you it's not true. I think I can pretty easily, okay? So here's what I'm going to do. I'm going to describe a function to you, all right? And I'm going to give you the number that I'm spitting out, okay? And I want you to tell me where the number came from, all right? Make sense? So what if I say 2 goes in, 4 comes out, okay? 2 goes in, 4 comes out. 3 goes in, 6 comes out. With me? Okay, so if I tell you now that 8 comes out, where did it come from? 4 because I'm doubling it each time. Now, maybe you didn't catch that. It's okay if you didn't. But do you understand what I'm saying? If 2 goes in, 4 comes out, I doubled that. It looks like I may have doubled that. If I say 3 goes in, 6 comes out, oh, I did double that, right? So if I tell you 8 comes out, you're going to say it came from 4, right? That makes sense. Let me give you another one. 2 goes in, 4 comes out, right? 3 goes in, 9 comes out. With me? Okay, 16 comes out. Where does it come from? It was -4. See, you don't know where to send it back to, right? You don't know, does it go back to 4 or does it go back to -4? Because both 4 and -4 get squared to become 16. That's an example of a function that doesn't have an inverse. You have to be able to tell me exactly where it goes back. Does that make sense, kind of? So it's going to turn out that not every function has an inverse. It's okay. We have ways to work around it. It's fine. But that's going to be in the next sections. All right. We're not quite ready for that yet. All right. So that's it as far as like the notes for today. What I'm going to do now in the next few pages is what I've done is I've copied problems out of the homework, out of the book. And we're going to work through some of these homework problems based on what we've talked about here today. All right. So the first thing we're going to look at, this is a page out of the homework, is going to look nothing at all like anything we've done so far. All right. But as I explain it, I think it's going to make sense to you. So this is number 9 and then number 10. We're going to do number 10. I'm going to leave the odd problems for you. All right. So let's start here. All right. So let me explain what the heck they're asking you here. Oh man. Okay. I hope that's big enough for everyone to see. Are y'all all right with that? I can try and make this a little bit larger. No, I can't. Stop. There we go. All right, that's about as good as I'm going to get it right there. Okay, so what this problem is doing is it's asking you to figure out, A, B, C, D, E, and F. They want to know what f of g of 1 is, what f of g of 2 is, and they're giving you this table to work off of. So here's how the table works. The top row are the inputs x. And then the next row is what you get when you plug this number into F. And then this one is what you get when you plug that number into G. So for example, if I ask you, what's F of -3? What happens if you plug -3 into F according to this table? You get 11, right? What would F of 2 be? Go to 2, it spits out 1, right? Understand? What would G of 0 be? Plug in 0 into the G function, you get 1. Make sense or no? Yes? Okay, let's look at A then. A is asking you to do F of G of 1, right? Now, by definition, doesn't this mean F and inside of that G, but inside of that 1? So it's like the 1 goes into the G first, right? 1 goes into G, and then that answer goes into F. So first tell me what's G of 1? G of 1. So go to 1 and then go to G, you get 0, right? So this should now turn into F of 0. And now what does 0 plugged into F give you? 5, right? 0 into F gives you 5. So the answer should be 5. We do another one. How about B? F of G of 2. So that means F inside of that G, inside of G goes the 2. So this will be fun. Let's just go around the room. All right. Can you see okay? All right. So do you understand the notation? Okay, so what's G of 2? -3. Okay, good. And then take that and plug it into F. 11. Everyone got that? Go ahead. Okay, so see this part right here, G of 2? That means you're going to plug 2 into G. So you go up to your table, the X is the 2, and then you look at the G. The G is this row, right? So if you plug 2 in to G, you get -3. And then now this -3 is now going to get plugged into F, right? So now you go back up here, -3, and plug it into F, and you get 11. Got it? Okay, good. You can do the next one. We'll see. We'll see. And let's just talk through it. It's okay. I mean, you're here to learn, right? It's not about trying to put people on the spot. So the difference here, G of F of X or G of F of 2 means G goes on the outside and then F of 2 is on the inside. Okay. So what would F of 2 be? F of 2 is -. So where are you getting that from? F of 2. You're going to 2 here? And are you going into F or into G? You did it into G, right? So F gets it first. 1, okay. So now you have G of 1. And now plug the 1 into the G. Zero. Make sense? Is anyone else a little bit unclear on this? You sure? You want to go again? I think if you do it one more time, I think you'll be like, yeah, I got it now. Okay, so the notation here means F gets the 3 first, and then G will get that answer. So what's F of 3? F of 3, yep, -1, right? F of 3 is -1, so G gets -1, and now plug -1 into G. 0. Got it? Let's just do one more. Let's do F. So F says to do F of 3. So that means F's going to get plugged into it, F of 3. So it's going to go through twice, right? So first, what is the inside? F of 3. What do we got? -1. So that becomes F of -1 now. Now plug -1 into F, and you get 7. Okay. Those are kind of easy once you understand it. Pretty simple. Yeah. Any questions at home? Let's look at the next question. We're going to do number 12 here. This is problem 11 and 12. It's the same exact thing that we just did, except instead of them giving us a table to look at, they're giving us the graphs of F and G. So let me just try and explain to you. I think a lot of you already understand this. If I were to grab, let's say this point right there, I know it's hard to see it. That's the point 6, 5, right? So which function does this point live on? It lives on the G function. So this is telling me that when I plug in 6 into the G function, it spits out what? 5. You see that? The X coordinate is 6. So that means when I go to 6, plug that into the G function, I get 5. Compare that to this down here, this point right there. That lives on this function, which is the F function, right? It says it here. So that tells me that when I plug 6 into the F function, I get 2. Make sense, everyone? Every single one of these points on here could be looked at like this. So let's try 12 part A. So I want G of F of -1. By definition, this means G and inside of it, f of -1. Okay, we'll go around, we'll continue. All right, go ahead, sir. What is f of -1? 1. So you're going to this one here, right? You're plugging in -1, so you're going to the left -1. You're looking for the dot, which is up here at 1. So f of -1 should be the y coordinate here, which is 1. Everyone got that? So this is now g of 1. And now you plug 1 into g and get what? 4. So you're now looking at the g function. You're plugging 1 into it. So you go to the right one, you go up, you look at the point up. Yep, there's 1 goes in, 4 comes out of the g function. Got it? Is clear? Let's do B. How about G of f of 5? So G on the outside, F goes on the inside with 5 in that. All right, sir, you're up. So what's the inside of that? What's F of 5? F of 5 is 1, so you're on the F function, which is this one, right? And you're going to 5, and you see there that spits out 1, good. And then you plug that into G, 4. We just did that up here, didn't we? G of 1 is 4. We got the same answer. Okay. All right. Moving along here, C, f of g of 0. How about Tavi? We'll do. I don't want to forget about my students at home here. Tavi, you there?
Yes, I'm here.
Can you see the graph? Okay.
Yes, I can see.
Okay, I'll move this over here so I can there you go. All right, so let's start with the inside. What's G of 0?
5.
G of 0, it looks like 5. Now, they didn't give us a point there, did they? Tried to trick us, didn't they? You plug 0 into the G function, it looks like 5. I agree. And then go ahead and do f of 5.
1.
1. There you go. Go to the f function, plug in 5, you get 1. Good. I think y'all are wanting me to just put like 100 of these on the test, right? Okay, how about let's squeeze D in here. D is f of g of 2, which means f, and then inside g of 2. Let's continue at home. F of, how about Amanda, you want to go?
Yes, sir.
Okay.
Okay, so would it be 2?
G of 2, so we're looking at the G function, right? And
Yes.
we're looking at 2, and it spits out 2, yeah. And then f of 2.
So it would be would it be -2?
Good, -2. So you're going to the f function, which is this one. You're going to 2, and it spits out -2.
Yes, sir. Okay.
Okay, good. All right, I think y'all got that. That's my feeling, is that y'all understand that. What do y'all think's easier? Is the looking at the graph easier, or do you think the looking at the charts easier?
I'm very
Yeah.
visual. I like a graph.
Yeah, it's usually like 50-50 split with people. I mean, some people like the chart, some people like the graph. Well, okay. So that is the first set of assignments. So what I'd like for you to do, like I said, I'm going to send you this whole thing today. What I'd like you to do is number 9 and number 11. So I'm doing the evens here, but I will highlight them. That way, when you get it, you'll know what I'm expecting. Look at number 9, look at number 11. And this is just practice, of course. I'm not collecting it. All right. All right, next thing. Yes. On the Canvas thing? Yeah, no, I've, at least for these sections, kind of abandoned the online homework. I've just been giving you homework from class. What do y'all prefer? I mean, do y'all like the online homework? I mean, me personally, if like this was like was supposed to be a face-to-face class, right? I would never have done homework online ever if we were a true face-to-face class. Everyone's here every day. I would just ask you to bring your homework with you, and I would just walk around and give you a quiz grade saying, oh yeah, it looks like you did your homework. You did your homework. You know, that's the way I would do it in a normal class. The whole COVID thing messed everything up. So in case we ever had to go completely Zoom, I had to have it in place. I prefer this personally. All right, next set of problems. Okay, now I realize that these are hard to look at because it's kind of small. So what they're asking you to do is do parts A, B, C, and D. They want you to do f of g of 4, g of f of 2, f of 1, and g of 0. And it's for every single one of these problems, you're supposed to do that. And every single one of these problems has 2 functions in it. So let's just ignore all the odd ones for now. Look at the even ones. I'm going to do 2 out of this set. So looking at just the evens here, I want to make this, I don't know if I can make this big enough. Looking at the evens here, I can't get them all on this screen. Try to make it a little bit smaller. There. Looking at the evens, I'm going to let y'all go ahead. Oh, wait, all the evens are on one side. Stupid. There we go. Looking at those evens, I'm going to let y'all pick 2. Any volunteers? 20? Okay, I'll do 20. And then what other one do y'all want? 20 and 22. You're going to pick the hardest ones, right? That's fine with me. I don't care. All right, we'll do 20 and 22. So I'm going to need to know those 4 things for these, right? Let me go ahead and copy this. Put it here. Zoom out. And then I need to go back and get the instructions. Okay. All right, ready? Let's do part A. F of g of 4. F of g of 4. F of g of 4 means F, and then inside of that is g of 4. So let's see if we can do this without actually we're not going to actually figure out what f of g of x is. We're just going to see if we can use the functions right now. So what would g of 4 be? You go to the g function, you plug in 4 into this. What would you get?
1/6.
3 over 18, which is 1/6, right? It reduces out. So this would be f of 1/6. Is everyone clear with what I just did? We're doing this kind of mentally. We're going to do it mentally as far as we can. And now 1/6 goes into here, right? So that I should just write down. That's going to be the absolute value of 1/6 minus 2. And to put those 2 together, I should get a common denominator. Absolute value of 1/6 minus 12/6. And that's going to be absolute value of negative 11/6. And the absolute value of any number is the positive of that number. So you should get 11 over 6. So just to recap, 4 goes into G first, that answer goes into F. So 4 went into G, we plugged in 4 here, squared it got 16. 3 over 16 plus 2 is 3 over 18. That reduces to be 1/6. That answer goes into F, and we get 11/6. Let's do part B. B, we're going to do G of F of 2, which would mean G on the outside, F of 2 on the inside. All right. So let's continue in here. I forget who finished last. You finished? Okay. Is it Josiah? Yes. Okay, Josiah, how do you feel about this? Starting on the inside here, f of 2. It should give you 0, right? You plug 2 in right here to f, you get 2 minus 2 is 0, the absolute value is 0, 0. Okay, so this is g of 0. All right, and what happens when you plug 0 into g now? 3 over 2. That making sense, everyone? 2 more. F of 1. F of 1 means f goes inside of f, and inside that f inside, you get a 1. All right, Carissa, right? Carissa, there, I think you can see it all. Yeah, so when we plug 1 into f, you get 1 minus 2, it's -1, but absolute value, which would be 1. Okay, so that's 1. And then you plug 1 in again. Same thing, 1 again, right? In more advanced math classes, we would call 1 a fixed point of this composition, meaning that if you continue to compose f with 1 over and over, it just keeps looping back to itself. It's just 1, 1, 1, 1, 1, 1, 1. It's called a fixed point. And in computer science, that we use this idea of a fixed point to actually do some pretty cool things. All right, good. Last one, g of 0. This one might be the hardest one. Let's see. Let me grab g and bring it down here. So g of 0, if we do g of 0, okay, at home, Juan, you're up. If you're there. No? Juan, no? Adam, are you there?
Yes.
Are you following, Adam?
Kind of, yeah.
Okay. Do the inner one here. What's g of 0?
That would be 3 over 2.
Okay. And now we got to take that answer and go back into g with it, right? So that's not as obvious. We'd have to actually do 3 over 2 squared plus 2, right? That's 3/2 back into g. This is not a fixed point. I don't believe this is a fixed point. Let's see. We square 3/2, it gives us 9/4 plus 2. We have to get a common denominator. 3 over 9/4 plus 4/2, sorry, not 4/2, 8/4. Trying to get a common denominator between the 9/4 and the 2. So I've turned the 2 into 8/4. Now I can put those together. That'll be 3 over, what is that, 17/4. And just remember, this really means 3 over 1 over 17 over 4. That's what that means, because the big division bar is here. So we rewrite the 3 as a 3 over 1, and then you can turn that division of fractions into multiplication of the reciprocal. This becomes 3 over 1 times 4 over 17. And this gives you straight across multiplication, 12 over 17. All right. Yes? So far, it's pretty okay. All right, what was that other one? Let's see. 22, right? Make this bigger here. All right, let's do this. I'm going to let you work these. Okay. See how quickly you can get through these. I want to remind you of something though, before you actually go and try and crank this all out. X to the 3 halves. What this means, you can look at this one of two ways. You can look at this as being the square root of x cubed, okay? Or you can look at it as being the square root of x cubed. Either way, that's what the 3 halves power means. That comes from a property of exponents that says x to the m divided by n is equal to the nth root of x to the m, but that's also equal to the nth root of x raised to the m. All right, that's the property I'm using there. Just going to remind you of that. Now, why don't we take, I don't know, how much time do you think you're going to need for that? Six minutes? Let's see how much you can get in 6 minutes. Find f of g of 4, g of f of 2, f of 1, g of 0. I'm going to step away for just a minute. No issues? Did you finish? C and D? Do you have a problem with the other? Oh, were they just messy? Yeah, they're just ugly because they're like not real nice numbers. Yeah. Let's do A together and then we can talk about the others. You all ready to do that? Okay, so I'm going to get rid of this because we don't really need this. Okay, so if I'm going to do f of g of 4, that's f, and inside of that, g of 4. So that's f. Now, when I plug 4 into g, 4 plus 1 is 5. I get 2 over 5. So 2/5 here, right? And then that goes into f, but all f does to that is takes that and raises it to the 3/2, which is the answer. You could put that as, if you wanted to, you could write it as the square root of 2/5 cubed, right? Or if you wanted, you could write it as the square root of 2/5 cubed. Now, because calculus is eventually where you're going, this is fine, okay? Questions? Same with the part B. If you do part B, you're going to do G with f of 2 inside of it. When you do f of 2, let's see, when you plug 2 in here, you get 2 raised to the 3/2, right? Okay, plug that into G, you get 2 over 2 to the 3/2 plus 1, which would be fine. If you wanted to, this actually, you can figure out this, you can do something with. I mean, this is fine as an answer, but you could look at this as being 2 cubed square root. And 2 cubed is 8, right? So square root of 8, if you wanted to, you could write it that way. So you could put 2 over root 8 plus 1. And there's all sorts of other things you could do, to algebraically to change this, but I think that's okay, just like that. All right, so I don't want to work these next two out. Anyone want to tell me what f of 1 was? It's just 1. Okay, and how about g of 0? 2/3? 2/3, okay, that's what, so f of 1 is 1 and g of 0 is 2/3. Okay, I have one for you. What would f of g of -3 be? So who gets -3 first? G? Okay, so if I plug -3 in for g, what do I get? I get -1. Plug that into this. You can't, right? So this becomes f of -1, but that becomes -1 raised to the 3/2. And what's wrong with that? Why can't I do this? Can't have a square root of a negative. So what would you say to f of g of -3? It's what? Undefined. This would be undefined. I was hoping that would happen here when y'all picked the problem, but it didn't. So I wanted to make sure you saw one where, you have no problem plugging -3 into g. That's not an issue. It's the output of the g that is messing up the f. Does that make sense? Okay. All right. How are we doing on time? All right, we're good. We're good. Cranking along here. We just did those two, right? I would recommend that you do, I don't know if you need to do all of these, but, wouldn't hurt to maybe do like, 3 of those 5 odds, or do them all. Shit, I'm not stopping you. Okay, next concept. In problems 23 through 38, find f of g, g of f, f of f, g of g. So that means we actually have to do the algebraic composition of each one, and then we have to state the domain of each one. So we did some of these earlier, right? Right? When I was first talking, we did a couple of compositions and we found the domains where we had to check those two things. Here's a big group of problems for us to do the same concept to, but we have to do 4 different compositions. So let's look at these because this could be messy. Let's do some evens. What do you say we do? I don't know. What do y'all want? Look at 24 and 26 and 28. Are any of these going to have domain issues? None of these are going to have domain issues, right? None of them. Because you never have division by 0. You never have square roots of negatives. So I think 24, 26, and 28 are probably all just like tedious problems. So if y'all are okay with that, I think maybe 30 would be probably the best place to start here. All right, so I'm going to do this. Yes. That's right. There wouldn't be a problem. So you should have for domain, yes, all real numbers. You should. And you'll see when you work it out, like you have when you check the two things, there's no issues on either one. So it's going to be everything, right? Yeah, so if both functions have all real numbers as their domain, then the composition will also have all real numbers. You can think about it like this. If you can plug anything into, let's say you're doing f of g of x. So g gets x first. If g can handle anything, right? And the output of g is being plugged into f, and f can handle anything, then there's nothing that's going to stop you. Your original domain on g is your domain for the whole thing. The range is different. The range is different. Range of compositions is a lot harder to do, and that's why we're not asking. Yeah, it's only domain. Let's see here. All right, so I want to just make sure I copy down the instructions, which are to find these things right here. All right, here we go. Let's start with A. Let's do f of g. Okay, so for part A, what we really want to do is f of g of x. That means we want to take f, plug g into that. Okay, things are going to get messy. Here we go. G of x is -2 over x. Right? That's the g function. That gets plugged in to f, right? So when I plug that into f, I get 1 over -2 over x plus 3. Does that make sense to everyone here? The g function goes into the f function wherever that x is. There it is. Now, for this, that is our answer, right? That is our answer, is the composition. Let's talk about the two things. First of all, I'm going to look at the domain of what? G, because G got X first. So the domain of G, what can you tell me? Everything but 0, right? Because you have -2 over X. X can't be 0 or else we got division by 0. So everything but 0, that's -infinity to 0 union 0 to infinity. Now the second part and the hard part, which is that we need to make sure that whatever comes out of G, right? Whatever comes out of G, this output, when it gets plugged in here, what do we have to guarantee about all that stuff? That's not the whole thing is not 0, right? So in other words, you need to look at this denominator and you need to make sure that that's not 0. So I need to figure out when this is not 0, which means I'm going to go look and see where it is 0 first. And then I'll throw that answer out. So -2 over x plus 3. When is that 0? So how would you solve this? You just plug in a number?
Move
What
the
number?
3 to the other side.
Yeah, let's move 3 to the other side. Let's do it algebraically. Move 3 to the other side so it becomes -3. Now what? Careful, X is on the bottom there, not on the top, right? Multiply everything by X, okay? Multiply everything by X, right? Everything by X. So if we multiply both sides by X, the X's will cancel on the left. You get -2 equals -3X, right? And now finally, to divide, I already gave it away. To get X by itself, you divide both sides by -3. And so you get X is what, positive 2/3? And that's what X can't be, right? X cannot be this. So if X can't be that, then I would say that we would have everything except 2/3. So this says everything except 2/3. This says everything except 0. So what do they have in common? Everything except 0 and 2/3, right? Those are the two numbers I can't plug in. So I think the final domain on this would be, it's going to be a couple of intervals, isn't it? If you want to look at it like a number line, here's 0, here's 2/3, right? We cannot have that. We cannot have that. We can have everything here, everything here, everything here, right? Just not those 2 points. Those are open circles. So that would be -infinity to 0, parentheses, union 0 to 2/3, parenthesis there, union 2/3 to infinity. Yes? All right. I think you could handle G of F. I want to do F of F. Okay, I'm going to skip to C. I want us to do F of F. So if I do F of X, this will be F with F plugged in. Now F is up here, so I'm just going to copy F real quick. There's F. All right, so the first thing that happens is that we plug F of X into itself, right? So here is F of X inside of F. Now I'm going to take that, plug it into F again. And so everywhere I see an X, I replace it with that expression. So it's going to be 1 over this whole thing, right, is the new X, 1 over X plus 3 plus 3. And now let's talk about the two things that we need to. First, we're going to look at the domain of F because both of these are F, right? So domain of F, what can we not have? Can't have -3, right? X can't be -3 or else we have a problem. So instead of writing the interval, I'm just going to tell you what it can't be. X can't be -3. Now let's talk about the composition part. So whenever you look at this output, that output here goes right here, +3, and we need to make sure that that is never 0, right? That thing can never be 0. So we want to figure out when is 1 over X plus 3 plus 3 equal to 0. We're going to figure out where that is, and we're going to throw that answer out. And I would do this the same way. I would move that 3 to the other side. I would multiply both sides by X plus 3, which would give you 1 equals -3 times X plus 3. Distribute a -3. You got a little linear equation there. Add 3 to both sides. And divide both sides by -3. X can't be that, right? -4/3. So we can't have -3 go in, and we can't have -4/3 go in. Are there any questions on the steps here? Oh, I did x plus 1. Uh-oh, why did I do that? I wasn't paying attention, I guess. I saw the look on Chris's eyes there, like glaring at it, like, what the hell? Okay, yeah, I messed up. I was supposed to do x plus 3 on both sides. I have no idea why I wrote x plus 1. And so that changes things over here, right? This becomes a -9. And then when we add to both sides, we get 10. And so you get -10/3. I was about to check it, but yeah. All right, so everything except these two numbers, right? And I think you could convince yourself this is true, because look, if I asked you right now to do f of -3, right? If I asked you to try and do that, first thing you do is try and plug -3 into f. And you can't, right? It's undefined. So that won't work. And also, if I try and do f of -10/3, what happens? If you plug -10/3 in, right there, what would you get? I'm going to have to do it on the side here. 1 over -10/3 plus 3. What would that be? Where? Say again. Oh, here?
Yeah.
Yes, you could. But what I'm saying is, remember how the problems before this, we were given a function and we were asked to find like what's f of 1. So you just plugged 1 in here and then 1 and then sent it through again. That's what I'm doing. I'm just verifying that when you plug -10/3 in to this, you take that output and plug it in again, you're going to get undefined. Or plug it in right here. Either way. Okay, I'm kind of running low on time here for what I still want to do. Let me see here. Do y'all want to do more of these, or do you feel like, I feel like 38 looks like a disaster. Doesn't 38 look like a disaster to you? It does to me. Let's do 38. And I won't do them all. I'm just going to do a couple of them. So here's the functions. And the instructions are the same instructions. So I want to do these with the domains. All right, we'll start with A. We'll do f of g of x. So inside of f, we're plugging in g. G is ugly. G is x plus 4 over 2x minus 5. Right? That's what g is. And that g right there is about to get plugged into x. I'm sorry, in for x into the f function. So it's going to go here and here. That big ugly yellow fraction is going to replace both this x and this x in the f function. So it's going to look terrible. It's going to be 2 times that g function minus 1 over the g function itself, x plus 4 over 2x minus 5 minus 2. So as bad as that looks, we can start talking about domain. First of all, I'm going to look at the domain of G. And what can you tell me about G? What cannot happen with G? Denominator can't be 0, right? So we could just figure out what that is. 2x minus 5 equals 0, right? We just ask ourselves, when is that 0, right? Well, this right here is going to be 0 if you move 5 over and divide by 2. 5 halves, we want to throw that out, right? We don't want 5 halves to ever get plugged in, or else G is going to fall apart, right? Now we got to make sure that when you do the composition and this thing goes into F, right, that we don't have any problems. Well, F will have a problem if this thing is ever 0, which means if this thing is ever 0. So I need to solve that, figure out when that's 0. So my second step is to figure out when x plus 4 over 2x minus 5 minus 2 equals 0. And I just play that same game, right? I move the 2 over to the other side. I'm going to multiply both sides by 2x minus 5. Distribute. And now I have a linear equation. So I just solve for x. I'm going to move all the x's to the right side. So I subtract x on both sides, gets 3x. And I'm going to add 10 to both sides, which gives me 14. And then I'll divide by 3, and I get 14/3. X can't be this. Which number is bigger, 14/3 or 5 halves? Which number is bigger? How did you do that? Do you have a way of doing that? Is 14? So here's a quick way to check fractions. If you have two fractions and you want to know which one is bigger, okay, which one is bigger than the other, all you have to do is multiply across like that, 15, multiply across like that. This is what, 28? This number is bigger, which means this fraction is bigger. That's a quick way to check two fractions, see if they're, which one of them is bigger. You know why that works? Think about this. If I asked you to take these two fractions and get a common denominator, what would you multiply on the top and bottom? 3. And then what would you multiply on top and bottom here? 2. Now, what are they both going to have the same denominator, right? So all you're really doing is comparing the numerators, which is exactly the same as what happens when you go across like this. This 3 times 5 is the numerator over here, and this 2 times 14, 28 is the numerator over here. So whichever one is bigger is your bigger fraction. Okay, now the reason I asked you which one is bigger, because I have to put these on a number line. I don't need to draw this, but just so you're clear on how I'm going to get my final answer, 5 halves is to the left of 14/3. And I don't want those as part of my answer. So everything over here, everything. So it'll be negative infinity to 5 halves, union 5 halves to 14/3, union 14/3 to infinity. All right. We somehow avoided problems that had square roots in them. We avoided these. I'm looking at the clock. Yeah, I think this is going to be probably a good place to stop. The next thing we need to talk about is doing, remember when I told you that what if we have this unique situation where we do composition f of g of x, we get the same answer as g of f of x, and they both spit out x. These problems, what they do is they ask you to verify that that's true. So they ask you to figure out what f of g of x is, and then g of f of x, and they want you to show that both of them give you x as an answer. So I would say try a couple of these odd ones. And then the last thing here is this. I will hold off on this. And in the book, if you see a symbol like this next to the problems, that's because in calculus, this means this is a concept in calculus. You're going to have to do this in calculus. So I'll save that for next time. I think we have enough on our plate. Let's look at the review real quick, just because I haven't even talked about the test that's going to be next Monday. So this is the review that I sent out. So I do not believe that your test can possibly be this long. I don't know. I think it's too long. I haven't tried to do all these problems in an hour and 40 minutes, but this gives you kind of a flavor of what to expect. So remember that we did cover in the beginning transformations. So I'm going to ask you to graph something, and that means you're going to need to know, like, what does this -3 do? What does this +4 here do? What does that -2 do? And you're supposed to list all the transformations. So in this one, like, for example, can someone tell me what the transformations are for this one? In the order that you need to do them? Left 4. Okay. Flip it over the x-axis. Stretch it out by 3, so it stretches vertically that way, and then whole thing down 2. So I would expect you to say, you know, shift to the left by 3, reflection over the x-axis, vertical stretch, shift down 2. So you would list the transformations, then you would sketch the function. Once it's sketched, oh, you also have to know what the square root function looks like, right? So once you've done all that, you should be able to tell me what the domain and range is just by looking at it. Okay. This one, I give you a quadratic function and I ask you to convert it to standard form, which means you will have to do what? Complete the square. So you'll have to go back in your notes when we talked about complete the square, but I will remind you, the very first step for completing the square is to make sure the number in front is a 1. And if it's not a 1, you have to factor it out. So just look in your notes, look at the videos. We did talk about how to do this. Once you have it in this form, if you know what H and K are in A, then you know it's a parabola that's been shifted up, down, left, right, and maybe flipped over. Once you know that, you can state the domain and range easily. So that's kind of like problem 1 in the sense that there are like transformations, but you have to do the completing the square first before you can see the transformations. When we get to 3, that's when you want to follow those steps that I did in class. So go back and look at all the different steps for graphing a quadratic. Remember what they were? Does it open up or down, right? What's the vertex? Quick sketch. Does it have x-intercepts? How many? Go find the x-intercepts if you have any. Y-intercepts, draw a picture, right? Number 4, polynomial function. This is good news and bad news. Good news, it's factored. Okay, so you can figure out by looking at this where the x-intercepts are, and you can also tell me if it bounces or crosses just by looking at this. The only thing you don't know is the left and right behavior, which you have to kind of analyze that to figure out. Again, we did some of these. This one, numbers 5 and 6, those are polynomial functions you have to sketch. The hardest part of those is setting them equal to 0. And both of these have to be done with, what's that thing called? synthetic division. So you have to do that not leading coefficient, that rational zero test where you create the list of numbers, do the synthetic division. And remember what I promised you. You'll get answers for synthetic division. It'll work within the first few numbers, right? Like if your list has like 1, 2, 3, 8, 9, like it's going to happen in the first few. So if it doesn't, something's wrong. Like something is wrong. Numbers 7 and 8 are rational functions. So there's a whole set of steps on how to do that, right? And yeah, so yeah, there's a whole bunch. And I think this one's pretty clean because it's easy factoring. Don't forget to look for holes. All right, and then on this one down here, I think the denominator, you have to use the synthetic division to factor that out. And then inequalities is what we did at the end of class or last time. All right, so here's what I'm gonna do. I'm gonna allow you to have a formula sheet, okay? One 8.5 by 11, 8.5 inch by 11 standard sheet of paper, front and back. You can put any formulas, any steps, any procedures on that sheet, okay? I'm not going to penalize you for having it. I think last time, didn't I penalize you if you wanted one? So I won't penalize you. If you don't use one, I will reward you with a 5-point bonus just to start, okay? So if you feel like you don't even need it, then you're going to get 5 points. And if you're one of those people who don't need it, and you're only like 1 or 2 of you that don't need it, I might up the bonus a little bit more, okay, to make it really worth it. So minimum of 5-point bonus. But if you need it, that's fine. Just make sure that on your reference sheet, let's not call it cheat sheet, on your reference sheet, if you're going to use it, don't work out any problems. Don't have examples worked out, okay? It's only steps, procedures. So if you need to write down all the steps for graphing a rational function, the horizontal asymptotes, the things you check, write it all down. That's fine. Just don't work any problems out. And I will collect those with the test. I'll probably just walk around and check them off before, as you're doing the test. Any questions? Okay. Have a good weekend. Yes. Can you do what? White, just a blank sheet? Yeah. It doesn't have to have lines on it. Just make sure it's a standard sheet of paper. Front and back. Shit. Yep. Okay, have a great one. Not like I just broke that. All right, thank you. What the heck? That's really weird. Huh. Strange.